In this presentation on sets, we are going to talk about operations on sets. We start this presentation with the term Venn diagram. So suppose we are given two sets A and B, and the universal set corresponding to these sets, it is the set U, and further it is being given that A is a subset of B. Now we want to represent this situation using some diagram, and suppose we present this situation in this way, where we are saying that this rectangle we have, it is representing the universal set U. Then we have the subsets A and B of this universal set. They are represented with these circles. We are having this circle, we are saying it is representing the set A. This circle, it is representing the set B. Set B means we are saying the region inside this circle, that is representing the elements of A. The region inside this circle, it is representing the elements in B. So clearly every element of A is an element of B. It means that this figure or this picture, it represents the situation that A is a subset of B, and the universal set we have, it is U. So this kind of approach or this kind of diagram, this is called Venn diagram. So we are saying that the pictorial representation of the relationship among sets by mean of a diagram is called a Venn diagram. And when we are talking about the Venn diagrams, we are having some fixed procedure, and that includes that the universal set is always represented by rectangular regions, and the subsets of this universal set, they are represented as the circles inside this rectangle. So this is what a Venn diagram is. Now we come to the operations on sets, and the first operation we are going to discuss, it is the union of sets. So suppose we are given two sets, one is the set A and other is the set B. Then the union of these two sets, it is denoted by this symbol, and it is, we are talking about when we are writing A union B, it is A itself a set which contains the elements. This set, it contains those elements which are either the elements of A or the element of B, or we are saying both A and B. So we try to understand this definition with an example. Suppose we are having the set A, it has elements 3, 4, 5, 6. We are talking about another set B, it has elements 4, 6, 8, 10. So when we are talking about the set A union B is, this set has elements of A. We are saying it has elements 3, 4, 5, 6. Further, it also has the elements of the set B. Now 4 is, we are saying 4 is already written over here. The 6 is already written over here. So we are writing it has elements 8 and 10. Further, it has elements 8 and 10. So we are saying A union B, it has elements of A, it has elements of B, that is both A and B. So if we represent this situation using the Venn diagram, we have the situation in this way. So we are saying we are considering the case of A union B, particularly when we are saying neither A is a subset of B nor B is a subset of A. So what this diagram represents is that A union B, when we are talking about, this portion is the set A, this portion is the set B. So A union B means that any element that is in A, it lies in A union B. Any element that lies over here, it lies in A union B. So what this diagram is representing, it shows that A union B contains all elements of A as well as all elements of this set B. So from this, what we are saying is that A union B, that is equal to, we are saying it contains all element X such that X belongs to A or X belongs to B. And we can see this result in this form. We are saying that X belongs to A union B. X belongs to A union B means we are saying that X lies somewhere in A union B if and only if we have X belongs to A or X belongs to B. So these all conditions, they are equivalent conditions. Now we move on towards another example over here of the union of sets. So suppose we are having the set A, it has elements X, and X is a prime number less than 10. There is another set B, it has elements, we are saying X belongs to N, and X is a factor of 12. Now when we are talking about the set A, we are saying prime numbers less than 10, prime numbers less than 10, they are 2, 3, 5, 7. When we are saying set B, it has X is a factor of 12. So factors of 12, they are 1, 2, 3, 4, 6, 12. Now when we are calculating A union B, we have all the elements of A, all the elements of B. We are saying we are writing A union B in this form. So all the elements of A as well as the elements of B. Now the first element, we are writing it as 1. It is in this set B. We are writing the elements over here. We have written 1. Then next element we are writing it is 2. 2 we are writing. 2 is present in B. 2 is present in A. So we are writing 2 only once. Because we know that when we are talking about sets, the repetition of elements, it doesn't make any sense. Next we are talking about the next element we have, it is 3, then 4, then 5, 6, 7 and 12. So this is the union of the sets A and B. Now the next operation we have, it is the intersection of sets. So for two sets A and B, the intersection, it is denoted by this symbol. We're talking about this symbol, it is representing A intersection B, and it is the set of all elements which are common to both A and B. So we are saying that A intersection B, it is equal to X. It consists of elements X such that X is an element of A and X is an element of B. The difference in intersection and union in these terms, we are saying when we were talking about the union, it was OR over there. That is either we have X belongs to A or X belongs to B or X belongs to both A and B. But in this case, we are saying that we have those elements in the intersection of A and B for which X belongs to both A and B. So we look at an example over here. Suppose we have the set A, it has elements 1, 3, 5, 7, 9. We have another set B, it has the elements 2, 3, 5, 7, 11, 13. So when we are talking about the intersection of these two sets, we are saying A intersection B. It has the elements that are common between these two sets. We are saying 1, it is not common between these two. 2 is not common between these two. This 3 element, it is present in both these sets. 5 is present in both these sets. 7 is present in both these sets. So we are saying A intersection B is equal to, it consists of the elements 3, 5, 7. So these are the elements present in both these sets. So if we plot this situation using the Venn diagram, if we draw the Venn diagram over here, we obtain the diagram in this form. And we are saying that this portion that is common to both the sets, the set A has elements 1, 9, 3, 5, 7. Set B has elements 3, 5, 7, 2, 11, 13. We're talking about this whole portion, it is representing B. This whole portion, it is representing A. And A intersection B is the region common to both A and B, and it has elements 3, 5, 7. So this Venn diagram for this situation, we are talking about this case, that when we have that A, neither A is a subset of B nor B is a subset of A, then this common portion that we have, it is corresponding to the set A intersection B. It corresponds to the set A intersection B. Now, from this discussion, we can infer two things. First is that an element X belongs to A intersection B if and only if X belongs to A and X belongs to B. And further, what we have is X does not belong to the intersection. We are saying if we consider an element which does not belong to the intersection of A and B, it means that X does not belong to A. We are talking about this implies us that X does not belong to A or X does not belong to B. So how we can understand this situation is, we are saying that X does not belong to A intersection B. It means that X does not lie in this region. It means that X cannot belong to both the sets A and B. So from this we can infer that X does not belong to A or X does not belong to B. Now next we are considering some examples over here. The first is, if A is equal to the collection of all those natural numbers such that X is a factor of 12 and B is the set, it consists of natural number X and X is a factor of 18, we have to find A intersection B. So X is a factor of 12, it means A is the collection, it has elements 1, 2, 3, 4, 6 and 12. B, X is a factor of 18. For the set B we have this condition. So we are saying B has the elements 1, 2, 3, 6, 9 and 18. These are the elements of the set B. Now we have to find the A intersection B. So A intersection B, it is a set and it is a set, so we put these brackets and we are saying that we are talking about the common elements between the two sets. So we are talking about the intersection of these two sets. So we are putting these brackets over here. Now the common elements we have, 1 is present in both these sets, 2 is present in both these sets, 3 is present in both these sets, 4 is present in only set A but not in set B, 6 is present in both these sets, then 12 is not present, 9 and 18 they are not present in both these sets. So we are saying that A intersection B, it has elements 1, 2, 3 and 6. These are the elements which are present in both the sets A and B. Next is, if A is equal to X such that X is equal to 3n and n belongs to Z. It means we are talking about all integers which are multiple of 3. And B is the set such that it has elements X such that X is equal to 4n and n belongs to Z. We have to find the value of A intersection B. So what this thing represents, we are saying X is equal to 3 and n belongs to Z. It represents that we have all those integers which are multiple of 3. The set B, it corresponds to all those integers which are multiple of 4. We have 4n over here, so these are multiples of 4. We have 3n over here, so these are multiples of 3. Now we are talking about A intersection B. So A intersection B means we are talking about all those X. We are saying X belongs to Z. We are interested in those values for which X is a multiple of 3 and X is a multiple of 4. We are saying X is a multiple of 3 and X is a multiple of 4. So if X, a number, is multiple of both 3 and 4, it means we are talking about all those integers which are multiple of 12. And we can write this set in this form. We are saying it is all those X such that X is equal to 12n, where n belongs to Z. So this is the set A intersection B in this case. Next is, if A is equal to the open interval 2, 4 and B is equal to the semi open, or you can say semi closed interval 3, 5, we have to find the value of A intersection B. Now if we look at these intervals, so the open interval 2, 4 means we are talking about the case that it is all those real numbers for which 2 is less than x is less than 4. Next, B is those real numbers for which 3 is less than equal to x is less than 5. So if we plot these on the number line, we obtain the situation in this form. We are saying the set A, it is open interval 2, 4, it has numbers from 2 to 4, and both these endpoints, they are excluded. Set B has elements from 3 to 5, this 3 is included, and it has elements up to 5, and this point 5 is excluded. We have to find A intersection B. It means we are talking about the region common to both these. So common region, we have this point 3 is included. We have all the points after this number 3 over here up to the number 4, but this 4, it is not included in the list because this 4 is not present in the set A, but it is present in the set B. So when we are talking about A intersection B, we are talking about those numbers which are present in both these sets. So we are saying the intersection of these two sets, it consists of all those real numbers which are greater than equal to 3 and less than 4. So we are writing that A intersection B is equal to x belongs to R such that 3 is less than equal to x is less than 4, and in interval form we can write it in this way, that it is a closed interval from 3 and open towards at the point 4. Next definition we have, it is disjoint sets. So two sets A and B, they are said to be disjoint if A intersection B is equal to 5. That is, there is no common element between these two sets. So in terms of Venn diagram, we can represent this situation in this form. We are saying that we have two sets. One is the set A, we have another set B. So when we are talking about A intersection B, clearly there is no common element between these two. So we are saying in this case A intersection B is equal to 5. It means these two sets, these are disjoint sets. Next term we have is intersecting sets. So we will say that two sets A and B are said to be intersecting if their intersection is not 5. So if the intersection of two sets is 5, they are called disjoint, and if it is not 5, then they are called intersecting sets. Now next we give an example in this regard. So suppose we have the set A, it has elements 1, 3, 5, 7, 9. We have set B, it has elements 2, 4, 6, 8. Then we have set C, it has elements 2, 3, 5, 7, 11. Then we have to find A intersection B, A intersection C, and we have to tell what we can conclude. So we are saying when we calculate A intersection B, so there is no common element between A and B. 1 is not present in B, 3 is not present in B, 5 is not present in B, 7 is not present in B, and 9 is not present in B. So what we obtain is that A intersection B, that is equal to 5. When we calculate A intersection C, we have these two sets, and the common elements in this case we have, it is, we're talking about A intersection C, so 3 is common, we have 5 is common, and 7 is common, and clearly this set is not equal to empty set. So what we can say is that the sets A and B are disjoint sets, whereas A and C are intersecting sets. So when we are talking about disjoint sets, we can consider two cases over here. The first case that we have already seen, we are saying that if A intersection B that is equal to 5, we are talking about A intersection B that is equal to 5, then this Venn diagram, we have shaded this portion A, we have shaded this portion B. This is representing A union B. Similarly, we can represent this situation in this way. We are saying if we have A intersection B that is 5. So A intersection B, if we represent, we are saying that both these are empty. So how we can distinguish these two cases? We are saying it is being given that A intersection B is equal to 5. It means set A and B, they are disjoint. So for the two disjoint sets A and B, this first Venn diagram, it is representing the union of these two sets. And for two disjoint sets A and B, this second diagram that we have over here, it is representing the intersection of these two sets. And as there is no point common between A and B, so there is no shaded portion in this case. Now the next question we have is, give an example of three sets A, B, C such that A and B are not disjoint, they are intersecting sets. B and C are intersecting. A and C, they are intersecting sets. But we have to show that A intersection B intersection C is 5. We have to give example of such a set. So suppose we are saying the set A, it has elements 1, 2. The set B, it has elements 2, 3 and 4. And set C, it has elements 1, 3, 5. Now if we calculate the value of A intersection B, then this 2, element 2 is present in A, element 2 is present in B. It means that A intersection B, it consists of, it is a singleton set with element 2. So it is not equal to 5. If we calculate B intersection C, so B intersection C means we are talking about, this is the set B, we are taking the intersection with C. What is the common element over here? The common element is 3. So we are saying the common element, it is 3. Again, this set is not an empty set. Next we are talking about, it is A intersection C. So A intersection C means we are talking about these two sets. And we are saying this, the common element now we have, it is this 1 is common in both A and C. So what we obtain is that this is equal to, this consists of, this set, it consists of singleton of one element, it is 1, and it is not equal to 5. So we are observing that these three sets A, B, C, these are the three sets which satisfy these three conditions. Now we are moving on to our fourth condition. Now if we calculate the value of A intersection B intersection C, we are talking about 1, 2, the set containing 1, 2, intersection set containing 2, 3, 4, intersection set containing 1, 3, 5. So there is no common element between all these three sets. When we are talking about these three sets, there is no element which is present in all these three sets. So we can say that this set is equal to 5. So this is the example in this example works in this particular case. Next is, give an example of three sets A, B, C such that A intersection B is equal to A intersection C, but B is not equal to C. So this is just like the cancellation law we are having for the numbers. We are talking about the situation if we have x plus y that is equal to x plus z, where we are saying x, y, z, these are the real numbers, then this implies us y is equal to z. But we are saying that this kind of result, it does not hold for the intersection of sets. So we are going to give the example over here. So suppose we are saying that the set A, it has the elements 1, 2, 3. Set B has the elements 3 and 4, and set C has the elements 3, 5 and 7. Now if we calculate the value of A intersection B, so A and B, the common elements we have, it is 3. If we are talking about the set A intersection C, A intersection C means we are talking about this set. The common element we have over here 3. So what we obtain, the common element, that is intersection of these two sets, it is 3. So from this example, we can observe that A intersection B, that is equal to A intersection C. But it is clear over here that the set B and C, they are not equal to each other. So we are saying that this kind of condition, or this property, it doesn't hold, calcination property doesn't hold for the intersection of sets. Now the next operation related to sets, it is the difference of sets. And for any two sets A and B, their difference A minus B, it is defined as, we are saying A minus B, it has elements X such that X belongs to A and X does not belong to B. So what we infer from this is that any element X will belong to A minus B if we have X belongs to A. What this thing implies is that X belongs to A and X does not belong to B. So we look at an example over here. Suppose we are saying that we have a set A and it consists of natural numbers which are factor of 6. So it has elements 1, 2, 3 and 6. Then we have the set B. It consists of natural numbers such that X is a factor of 8. So it has elements 1, 2, 4 and 8. Now if we calculate the value of A union B, it means we are talking about the set which contains the elements of A as well as the elements of B. So the answer we obtain, it is 1, 2, 3, 4, 6 and 8. When we are talking about A intersection B, so A intersection B means we are saying those elements which are present in both A and B. These are the sets A and B. The elements present in both these sets, they are 1 and 2. Next we are calculating the value of A minus B. So when we are saying A minus B, we are having these two sets. So we are talking about, look at this element 1 over here. We are saying from this set A, we are removing the elements of B. We have this 1 over here. So we remove this element from the set A. We have 2 in the set B. We remove this element from the set A. What we are left with is, we are left with is only 2 elements, 3 and 6. So we are saying that A minus B, it has 2 elements, that is 3 and 6. Now if we have to calculate B minus A, we are talking about again these two sets, we are writing B minus A. Now what we are saying, that this 1 is an element of A, so we will not consider this element of B. We have removed the element of B from this set. Then 2 is an element of A, so we remove 2 from this set. What we are left in this case, it is 4, 8. So this thing will be more clear to you when you look at this Venn diagram. We are saying that the set A has elements 1, 2, 3 and 6. Set B has elements 1, 2, 4 and 8. When we are talking about A minus B, we are talking about this portion. So what we have done, we have removed the portion of A that is common with B. So we are saying that this portion of the Venn diagram, it is representing A minus B. And when we are talking about B minus A, so we are saying we are considering that portion of B which is not intersecting with A. That is, we have removed all those elements of B which are present in A. So we are getting the answer as 4, 8. So this is the Venn diagram in the case of when we are considering the difference of sets. The next we have is the symmetric difference of two sets. So we are saying the symmetric difference of two sets A and B. It is denoted by this symbol. We are saying A delta B, and that is defined as, we are saying A delta B, that is equal to A minus B union B minus A. So this definition will be clear to you with the example. We are saying A has elements A, B, C, D. A set B is there, it has elements B, D, F, G. Now if we calculate A minus B, so we are talking about the collection. We're talking about the collection that is those elements of A which are not present in B. So those elements of A which are not present in B, they are shown over here. We are talking about this portion. We are saying this is the portion A, this complete portion is A. From this A we are removing this portion of B. So A minus B will have two elements, that is A and C. Now if we are talking about B minus A, so we are saying that this is the whole collection B that we have. We are talking about this one. We are saying this whole is representing the set B. From this set B we have to remove the elements of A. So the elements of A common with B, they are B and D. So if we remove these elements, what we are left with is the set G, F comma G. So this is the value of A minus B. This is the value of B minus A. Now when we have to calculate the value of the symmetric difference, it means we are saying that it is A minus B union B minus A. So union of these two sets, we are talking about A comma C and F comma G. We are talking about union of these two sets. So the answer we obtain, it has four elements A, C, F and G. So if we look at this Venn diagram, we are saying it has elements A, C and F, G. So this portion is excluded when we are talking about the set A delta B. Next we have is the complement of a set. So we are saying let U be the universal set and A is a subset of U. So whenever we are talking about the complement set, then we must know the universal set. Otherwise there is no meaning to talk about the complement of a set. Then we are saying the complement of A, it is denoted by this symbol, or we are saying it is A U minus A, and it is defined like this. We are saying that this A dash or complement of A, it consists of those elements of the universal set which are not the member of A. So look at this Venn diagram over here. Look at this diagram over here. We are having, this is the universal set. This is the set A inside it. So complement of A means those elements of the universal set which are not present in A. It means we are talking about the region outside this set A. So what we can infer from this is that X belongs to A complement. It means that X does not belong to A. So we look at an example over here. Suppose we are saying the universal set, it is 1, 2, 3, 4, 5, 6, 7, 8. And the set A has elements 2, 4, 6, 8. So this situation, it is shown over here with this Venn diagram. We are saying that U is the universal set. A has the elements 2, 4, 6, 8. Universal set has elements 1, 2, 3, 4, 5, 6, 7, 8. That is, it has all natural numbers from 1 to 8. Then A is the set of even natural numbers of from 1 to 8. Now the the complement of this set A, it means we are talking about those elements of U which are not present in A. So those elements are 1, 3, 5 and 7. So we are saying the complement of A, that is equal to U minus A. We are talking about U minus A. U minus A means those elements of the universal set which are not present in A. So we obtain the answer in this form. Now suppose we have to calculate the complement of A. So we have now the complement of A means we are calculating the value of universal set minus A complement. We are talking about universal set minus A complement means this whole set U, and A complement we have it has elements 1, 3, 5 and 7. It means now when we calculate this value, we are saying we are removing the elements of this set A from the universal set. We are removing 1, 3, 5 and 7. So what we are left over here is 2, 4, 6, 8, and that is equal to A. It means we are saying that complement of this set A, it is the portion outside this A, and the complement of this portion that is outside the A is the set A itself. Now let us consider another example. So we are saying let n be the natural numbers, set of natural numbers, and we are saying that A is equal to x such that x belongs to n and x is a odd number. Then we have to find the complement of A. So complement of the set A is all odd numbers. So complement of A in the set of natural numbers, it will be A dash, that is equal to all those x, all those natural numbers for which x is not odd, and if x is not odd, it means x is an even number. So we are saying the complement of this set will be all those natural number which are even. Now next we have is if A is a subset of U, where U is a universal set. First of all, we have to prove that the complement of universal set is 5. So if we look at this diagram over here, we are saying some set A is there, and this is the universal set that we have. This is the universal set and this is the set A that we have. Now if we talk about the complement of universal set, so complement of universal set means we are talking about all those x belongs to universal set such that x does not belong to universal set. So there cannot be any element that is element of universal set as well as not an element of universal set. So we are saying that this is equal to this set is empty. So this is the proof for this statement that complement of universal set is empty set. Next is the complement of empty set is the universal set. So we are saying the complement of empty set, that is equal to all those elements of universal set for which x does not belong to the empty set. So if x, we are talking about all those elements of universal set, x is an element of universal set and x does not belong to empty set, and we know that empty set, it does not contain any element. It means we are talking about the universal set itself. Next is we have to prove that complement of a set A, that is equal to A itself. So when we are writing complement of A, it means we are talking about all those elements of universal set such that x does not belong to A complement. We are, if you are not able to understand this, you can write A complement is equal to B. So we are technically writing the definition for B complement, that is equal to x belongs to U and x does not belong to B. So again replace this B by A complement, so you will obtain the definition in this form. So we are saying that this implies us this is equal to this set, that is equal to those x in U for which x belongs to A, because when we are saying that x does not belong to A complement, So we are saying that X is not in this portion, in this region. If X is not in this region, it means that X lies in A. So this thing is mentioned over here. We are saying X belongs to U such that X does not belong to A complement. So this term means that X belongs to A itself. So we are saying X belongs to U and X belongs to A. So it is equal to A. We are talking about all those elements in the universal set that belong to the set A. So that is representing the set A itself. Next we have is A union A complement is equal to U. So again, looking at this condition from a Venn diagram, what we have is, this is the set A. The portion outside this set A, it is the A complement. So union of both these sets, that is all the elements of the set A and all the elements of the set A complement together, they will form the set that is the union of these two sets. So how we are going to prove this is, we are saying A union A complement. So any element, it has elements X belongs to U. This A union A complement, this set will have elements X belongs to U such that X belongs to A union A complement. We're talking about this set. So we have union over here. It means we are saying that X belongs to U. When X belongs to A union A complement, it means X belongs to A or X belongs to A complement, because it is union. So we are writing OR over here. So if we separate both these terms, what we obtain is that X belongs to U such that X belongs to A or X does not belong to A. What this thing means is, we are saying that X belongs to A complement. If X belongs to A complement, it means that X does not belong to A. This is by the definition of A complement. We are saying X belongs to A complement means that X lies outside this region A. It means that X does not belong to A. So we are talking about those X in the universal set for which we are saying X belongs to A or X does not belong to A. It means we are talking about all the elements of the universal set. Next we have is A intersection A complement, that is equal to phi. So clearly we can see from the Venn diagram, when we are saying this is the portion A, this outside portion, this is the portion A complement. There is no common portion between A and A complement. So what we get is that A intersection A complement is phi. So algebraically we can prove it in this way. We are saying A intersection A complement, that is equal to the set consisting of elements X from the universal set. We have A intersection A complement. It means X belongs to A intersection A complement. Now what this intersection means, we can write that X belongs to A and X belongs to A complement. So from this what we get is, when we are again looking at this term, we're talking about X belongs to A complement means that X does not belong to A, because if X belongs to A complement, it cannot belong to A. So we are saying that this is equal to, this set is equal to those elements of the universal set for which we have X belongs to A and X does not belong to A. So we are talking about those elements which belong to A and which does not belong to A. So what we obtain from this, that there is no such element present in this set. So we are saying that this set, this value is equal to phi. This is an empty set. Next, these are the three sets given to us. One is the set A. It consists of elements A, B, C, D, E. Then we have the set B. It has the elements A, C, E, G. Next is the set C. It has the element B, E, F, and G. So if we plot these sets using the Venn diagram, we will have some situation like this. That the set A, it has elements A, B, C, D, E. The set B has elements A, C, E and G. Set C has elements B, E, F and G. Now we have to calculate the value of A intersection B minus C. So when we are talking about B minus C means, look at this portion over here. We are saying this complete, it is representing B. This complete, it is representing the set B. And if we remove these two elements from this set, we will get the elements B minus C. That is, it consists of the sets element. This set, it consists of elements A and C. So we have, this is equal to A, B, C, D, E. This is the set A. And we are taking intersection with the set with two elements A and C. So this is the value of B minus C. Now intersection of these two sets, the common elements we have, it is A and C. Next we have to calculate is A minus B union C. So when we are saying B union C, so we are talking about those elements which are elements of B, which are elements of C. So we are left with only element, that is D. So we are saying that B union C, it has the elements A, B, C, E, F, G. And the elements of A, they are A, B, C, D, E. When we are saying A minus B union C, look at this Venn diagram. We are saying this whole portion, it is representing B union C, this whole portion. We are saying from the elements of A, we are removing this portion. So the only element we are left over here, it is D. Or from these sets, you can see that A is already there in this list, B is already there in this list, C is already there, E is already there. So the only element of A which is not present in B union C, it is D. So in this case, the answer we obtain, that is equal to D. Next we have to calculate is A minus B intersection C. Again the set A we have, it is in this form. Now B intersection C, we are saying B intersection C, it has these two elements, that is E and G. These are the two elements which are present in both the sets B and C. So we are saying we are subtracting from it E comma G. So from G is not present in A, E is present in A, we are going to remove this element E because it is present over here. So the answer for this case we have, it is A, B, C and D. So we are getting A minus B intersection C, that consists of the set with elements A, B, C and D. Next we have is, if A is the set, it consists of the elements 1 by x such that x belongs to n, that is x, it is a natural number and x is less than 8. And B is the set, it is the numbers of the form 1 by 2n, x is a natural number and x is less than equal to 4. So if we write the elements of the set, we are saying x is less than 8, it means x has values 1, 2, 3, 4 up to 7. So A has elements, first element, if we substitute x is equal to 1, it is 1, then it is 1 by 2, then it is 1 by 3, 1 by 4, 1 by 5, 1 by 6, 1 by 7. And we are talking about the set P, it has the elements of the form 1 by 2x and x is less than equal to 4. So it is less than equal to 4. So first of all, we are going to substitute x is equal to 1. We will get the first element as 1 by 2. When we substitute x is equal to 2, we will get the second element, it is 4. When we substitute x is equal to 3, we will get it is 1 by 6. And when we substitute x is equal to 4, we will get it is 1 by 8. Now if we represent these two sets using the Venn diagram, we obtain this kind of representation. We are saying A has the elements 1, 1 by 3, 1 by 5, 1 by 7, 1 by 2, 1 by 4, 1 by 6. B has the elements 1 by 2, 1 by 4, 1 by 6 and 1 by 8. So these are the common elements that we have over here. Now if we have to write the value of A union B, A union B means we are talking about all the elements of A and all the elements of B. So the answer we can write it is 1, 1 by 2, 1 by 3, 1 by 4, 1 by 5, 1 by 6, 1 by 7, 1 by 8. So all these elements are there in this set A union B. Next we have is A intersection B. So when we are talking about A intersection B, the common elements we have over here, they are 1 by 2, 1 by 4 and 1 by 6. Next we are talking about A minus B. A minus B means we are talking about those elements of A which are not elements of B. So we are removing this portion from A. The elements of A which are not elements of B, this portion we are talking about. So the elements we have over here, they are 1, 1 by 3, 1 by 5 and 1 by 7. Next we are calculating the value of B minus A. So B minus A means all those elements of B which are not elements of A. So the only element we have it is 1 by 8. So we are saying the answer in this case it is 1 by 8. So if suppose we are calculating the value of B minus A, we can look at these terms over here. We are saying 1 by 2 is present in A, 1 by 4 is present in A, 1 by 6 is present in A, but 1 by 8 is not present in A. So that is why the value of B minus A, it is the set with single element 1 by 8. Next is, if R is the set of real numbers and Q is the set of rational numbers, then what is the set R minus Q? So if we look at this situation, we have the diagram in this form. We are saying we have the collection of whole numbers, or if we start with natural numbers, we will have the collection of natural numbers, then we have the collection of whole numbers, then we have the collection of integers, then we have the collection of rational numbers. The universal set we are considering it is the real numbers. We are saying R is the set of real numbers. We are talking about Q the set of rational numbers. It means when we are talking about R minus Q, we are talking about those real numbers which are not rational numbers. So the real numbers which are not rational numbers, they are called the irrational numbers. So the answer in this case, we are saying that R minus Q is equal to those X such that X is a real number and X is irrational. So we are saying that when we are writing the set of irrational number, we can write it in the form R minus Q. Next we have is, if the set A is given, it has elements 2, 3, 5, 7, 11, and it is given that B is the empty set, then we have to find the value of, first of all we have to calculate the value of A union B. Given is B is the empty set. So we can represent this situation in this form, the Venn diagram we have. So A union B means all the elements of A and as well as the elements of B. The set B is empty. So what we obtain from this, that the answer we have, that is the set A itself. Next is we have to write the elements of A intersection B. So clearly we are saying there is no element in B. So there is no common element between A and B. So we are saying that A intersection B, that is equal to 5. Next is, if A and B are two sets such that A is a subset of B, then we have to find number 1, A union B. So we can look at this situation in this way. We are saying this is the universal set. We have this is a set A, this is a set B, and set A is the subset of set B. Now we have to find A union B. So clearly every element of A is itself the element of B. So what we say, that A union B means all the elements of A We have to write all the elements of A and all the elements of B, but all the elements of A, they are already the elements of B, so we are saying A union B is equal to B. Second, we have to write A intersection B. It means we are talking about those elements which are present in both A and B. So if we consider an element over here at this point, we are saying it is element of B, but it is not element of A. So the elements that are present in A, these are the only elements that are present in both A and B. So A intersection B we obtain, that is equal to A. Next we have to calculate is A minus B. A minus B means we are listing all those elements of A which are not present in B. If we consider any element over here, it is always, if it is present in A, then it is always present in B. It means we can't find any element of A which is not an element of B. So we are saying that A minus B is an empty set.